Okay, here we are for lecture series number 4. This week for lecture 4, there are 2 components. We're doing pedestrian bridges and posts. The pedestrian bridges are on the heavier side. Posts are just a short one to kind of show you options and possibilities and kind of what really goes into the design considerations, because that's one of those ones that architects and landscape architects always have drawn on their drawings incorrectly, and sometimes they never actually see an engineer until maybe just before they're being installed or at the last minute, where they ask an engineer to say, the city tells them they need an engineer to sign off on it, to say it's been reviewed, and we can't because it hasn't been done correctly. So it's a small thing, but somehow it comes up again and again and again as an issue. So pedestrian bridges, everyone gets, needs an engineer and an in-depth look at it. So we're going to start with pedestrian bridges. We've both done several pedestrian bridges. Oddly enough, we don't have a lot of photos of them and access to all the drawings. Some of them are quite old and they're in a storage file somewhere, kind of off-site. Like I was thinking of the hockey, the ski pole.
The Kelso,
yeah, yeah. So there's a whole bunch more that we've done. We just didn't have ready access to all of the drawings and information. A lot of the kind of design concepts are similar to buildings for pedestrian bridges, like the engineering. There's a few cool surprises, and we'll show you with suspension bridges that one's just kind of a really unique thing, and that's a thought that we're going to talk about more next week when we talk about fabric structures as well. The kind of loading on bridges is more or less obvious if you've done structures 1, structures 2, and you've paid attention to the previous lectures in this series.
And certainly the process is the same. The process
is the same, yeah. So kind of talking about the loading conditions and things like that. So this one will be, these will probably be a shorter series of lectures, which is good because we're going tomorrow, or today's Monday, early, before the kids wake up. Tomorrow we're going to film the fabric one, so that we're actually a week ahead instead of 2 or 3 days behind. Mostly so that you guys have access to the first 5 lectures for your first assignment. Okay, go ahead. You can go ahead. I'm going to eat my toast.
Okay. So strength design for a bridge is very much like the strength design for a building, as Shannon implied before. We've got 3 main sources of live load. Obviously, there's the dead load, self-weight and finishes. And then there's 3 main sources of live load, same as in a building.
Remember, we don't talk about wind and snow as live loads anymore. He's doing it old school where they were subsets of live loads.
Right.
We just got to change that lexicon.
That's right. So to me, live loads include occupant loads, which are really what the code refers to as live loads, the weight of the people that occupy the bridge, the snow load, and the wind load that are applied on it. Those to me are the environmental loads. Seismic as well. Actually, we don't have those on the list because it tends not to govern bridges, but that's just because we're in a low seismic zone. Seismic can be significant in a place like BC.
It would have less impact than it might on some buildings, mostly because they're probably allowed to, like, you have to consider it and go through the design, and they probably have a big diaphragm component, but it's probably not as demanding on a bridge as it would be on a building, I would imagine. I'm not saying it wouldn't be, yes. But in California, seismic governs every single element in the building. For a pedestrian bridge, it probably wouldn't. It would be something you definitely have to check, but it wouldn't. It might govern some of the members. Lighter
weight and less stiff, right?
Exactly.
So the diagram that Shannon's incorporated here is a wind load diagram, and
they saw this from the GARD lecture too.
Oh, did you? Or did they? Okay, so you can see this constituent components of calculating wind load in the upper right-hand corner. The wind load is a force coefficient, which reflects the geometry of the thing you're looking at. The Q, which is your reference wind pressure. CG, which is your gust factor. So we are measuring hourly mean winds but the hourly mean wind is not representative of the peak wind. So we multiply by a gust factor, an exposure factor, which accounts for context, height above the ground, for example. And then the last two are H and L. That's just the projected area of the bridge.
And the one thing that this equation doesn't show, which I made sure to show you in the guard portion where I showed this image and kind of wrote out all of those things Dave just mentioned, was the importance factor. So IULS and ISLS needs to be in that equation. They don't show it in this because it also references this back to the main equation, and it says that you need to include that even though it doesn't show it in the writing. This is the same image they've been using for 25 years for ring walls.
At least. This hasn't changed in my memory.
Yeah. So they, rather than have someone redraw the image, they just changed the fact that because importance factors came into play in the 2006 code, I think.
That sounds about right.
They just put it as words above the diagram.
So serviceability criteria. So we obviously have to make it safe for strength. We have to make it strong enough for safety, and we have to make it stable. It can't tip over. But then we've got serviceability criteria. So it's got to be usable. It's got to be comfortable to walk on. Normal criteria would be dead and live L over 240 and live L over 360. This is about a number of things. It's about preservation of finishes. It's about tradition. It's about making sure that things that are straight remain visually straight, so that your eye isn't disturbed by excessive movement.
I would like to point out that same with all of the other things that we've talked about with serviceability, and these being the standards, that serviceability for a bridge, if it has no finishes to preserve, they might decide to throw these clauses out. This is where you'd start, same way you would for all of the other elements we look at designing. They're just a really strong suggestion. That's
right. It's written in non-mandatory language in the code.
And we will show you a type of bridge explicitly where they do exactly that. They say, forget, we're not going to follow these rules at all. And the whole premise is built on that. I have food in my teeth and I don't want to pick my teeth.
The other serviceability criteria for bridges is vibration. I think that Shannon talked about vibration in another lecture. They follow generally we follow the AISC Steel Design Guide. And essentially, you've got a whole vibration slide.
Yeah, that's in the specific elements.
Okay, so we'll elaborate a little bit later on vibration.
Yeah, and so they've already seen all the images, like they've seen what comes from the code.
Right.
The vibration one for bridges isn't as explicitly written out. Like it's the equation is there. It's the same equation that is kind of built off of the stair one. But it's more worked out in example, and you have to go back and extract it from examples that they do in their design guide. So it's slightly less, here's how you do it. So I've created a design aid and a spreadsheet, and in specific projects, I show you how I've done that. But you don't have, these are way beyond anything you guys have to do. It's not something that's expected to be done by you guys.
So just the little tiny refresher, what we're trying to do is we're trying to manage the acceleration due to vibration. So vibration, things go up and down. The faster the frequency, the more the acceleration in order to generate that wave. And the larger the amplitude, the more the acceleration. And it's the acceleration that you feel. If there was no acceleration, you wouldn't feel any force. So we're trying to manage acceleration. And we do that by finding the delicate balance of mass and stiffness. The higher the stiffness, the higher the frequency, but very high frequencies we are not sensitive to. So things above sort of 10, 11 hertz or 10, 11 cycles per second we're not sensitive to, and so we can tolerate higher accelerations in those. Increasing mass, lowers the amplitude, but it also makes us more sensitive to the vibration. So there's a tricky balancing act that has to happen. So we're going to look at a number of types of foundations, or types of pedestrian bridges. We started looking for precedents, trying to think about it and preparing a comprehensive lecture. The fact is that there are so many. Even if we look just in our own backyard, there are so many. So we focused on having a representative bridge of each major type, assuming that if what we're trying to do is inspire you, Google can take care of that.
Well, I mean, I show three of each. I show one of each of these kinds, and then the last half of the lecture is inspiration photos that we can talk about loosely.
So we'll look at a few different types. We can span with beams, we can span with trusses, we can span with cables. Those are kind of the broadly three broad types. Span with arches, I guess, might be another category.
Yeah, it's usually yeah, I'll add that. I just always think of it as not an arch on its own.
It's always an arch, and
it's always a truss. Really,
yeah.
It's just a truss where the bottom chord is flat, the top chord is the arch, and the cable, and there's cables that are
like
the
a web. So this is a nice place to start. A very, very simple bridge. This is a simple beam. A simple beam spanning across a gorge with wood decking. I want to point out that that this looks like an arch, and so you might be inclined to correct me and say, "No, Dave, that's an arch. That's not a beam." In fact, it's a beam. The distinction between an arch and a beam is not so much the curved shape, although that's part of it, but it's what are the boundary conditions. If the boundary condition can take an outward thrust, then it can behave like an arch. If the boundary conditions are allowed to move, then it has to behave like a beam, notwithstanding that it looks like an arch. So something shallow like this, the boundary forces would be huge. The outward thrust at each end would be gigantic and unmanageable. So it would be designed like a beam. The curvature is about getting enough height over the thing that you're trying to traverse over.
So that you don't have to have massive upstands here as well. It also means that when deflection happens, it's not as visible to the eye, so there's some built-in bonuses there. And to kind of validate Dave's point, you know that this is not taking outward thrust, because there's not a big, massive pier that it's connected, an abutment that it's connected into. But you can see that that is a Teflon bearing pad. You can see that it is being built to allow that to slip just a little bit at the end. And if it can slip a little bit at the end, it's for roller condition. And the roller condition means that it can't take that X direction reaction.
But it's an interesting thing to just start thinking about as we look at the precedents, because we don't make the distinction that the purpose of a bridge is to cross over something, and it's a different form if you're crossing over something that's a cut. So over a gorge would imply one type of form. If it's over an obstruction like a railway track, that would imply another type of form. So what you're traversing is going to dictate your form.
Might be a nice slide.
So this is another nice shallow arch bridge, and again, it's an arch. It gains no benefit from being an arch, except that it provides sufficient clearance underneath for whatever vessel needs to get under it. You might ask, why not just lift the bridge and have it flat? Totally valid, but you have to get up to the bridge, and so simply lifting the bridge means that you've got a big, long approach.
Or ridiculous sets of stairs. Anyone who's crossed any of the kind of built kind of stair elements that they have crossing the railroad tracks in Toronto knows that just to cross that short distance to get up that little bit of a height, there's like either a big set of stairs or, like Dave's saying, this massive, massive ramp that is way bigger than the bridge itself.
And you can't just have stairs, right?
Yeah.
Like if you're going to have stairs,
exactly.
you need an elevator.
Yeah.
And so that's a tremendous cost. And your ramp needs to be 1 to 20. So it's got to be a very shallow ramp in order to be accessible.
So we try to keep it as low to the ground at the ends as we possibly can.
So the shallow arch is a very pragmatic solution.
Slide, I just want to point out that this again is also not an arch, it's spanning, and that is detailed as a sliding connection as well. That's
right. I refer to it as an arch, but I'm speaking colloquially. It's an arch geometrically, not in its behavior. So this is an example of steel girders with a concrete slab as the deck, which adds mass, reduces the perception of vibration. This is a very common type of pedestrian bridge. It would be a wood deck with steel trusses. The Eagle Bridge in Canada make these. Lots of people make them, but Eagle Bridges are ubiquitous.
That rusty steel basic form look is who you've seen.
Yeah. Corten is extremely common for bridges because it's long life without protection, without relying on coatings. Now you can see that the bridge sticks up above the deck. Very common for the top chord to be at the top of guard, and then the bottom chord is as low as it needs to be to provide the depth for the bridge. So more often you would see the deck at the bottom chord elevation. This just happened to be a very long span, and so it needed a deeper truss. Shannon, do you want to share your philosophy on truss names?
Oh, I've shared that before. I think, names are helpful. We like to name things. It makes it easy to reference what you're talking about. Engineers will memorize every single type of truss they possibly can. That seems slightly like overkill to me. If you can do the math and you know what your kind of criteria for your site are, these things start to shake out. It's nice to have precedent, but people get like really worked up about having their last name on a truss.
I really like truss names. I find it's a nice shorthand. You can if you know the names of trusses, you say the name and you don't have to draw the web. Here's some that you will recognize: the Warren truss for sure. And the Pratt.
Don't forget that this is a mouse that you can hover over things, right?
Yeah, so you'll recognize the Warren, you'll recognize the Pratt for sure. You're going to see a child's truss or a long truss in some of these precedents as well. This hopped truss is really a triple whipple, isn't it, Shannon?
I think it, yeah.
So these are specifically bridge trusses. And then we've got suspension bridges. So a suspension bridge is really, the structural element is just a grouping of cables that run the length of the span and directly support the deck.
It is built on the premise that it moves, and that it moves a lot. So if the shape looks like this and someone is over here, it kind of goes like this, and then as you move across, the shape kind of goes with you. It's like walking across an elastic band, if you can imagine that. I mean, a taut elastic band, but the idea is that you do experience movement. You took our kids over, well, we'll show that picture of that bridge coming up.
Yeah, pure catenary has to take the shape associated with the load demand, and so it has to deform to respond to the load. The reason these things don't go from a curve to a point when you walk across it is because you're actually very light compared to the self-weight of the bridge, and so it's still going to generally take that catenary form because the superimposed load is small relative to itself. Which means these are appropriate for long spans, like very long spans, because the long span, you're going to be light relative to the bridge. A catenary for a very short span you're going to be heavy relative to the bridge, and it'll deform a lot more.
And so obviously no deflection criteria, or a very, very, very loose deflection criteria, because it is supposed to deflect. And vibration criteria becomes more about protecting the bridge, not about making people feel comfortable. The premise is that you're probably already pretty freaking uncomfortable when you're up there. A little bit of vibration isn't going to add to it.
Yeah. Yeah. And
I've walked across this bridge, and probably a bunch of you have, and
you feel the move for sure.
Yeah, I was uncomfortable. And if you've watched Shrek, Donkey does not like it at all. So now I'm just going to go through some bridges with drawings. I'm going to talk about one of them, and Dave's going to talk about one of them. The first one is the Dufferin Grove Park boardwalk, and we're going to call it a boardwalk because it's not a bridge. It is low to the ground, and the building department had very, very specific rules about it being a bridge versus a boardwalk, about what they were allowed to build on the site. So we've kept it within the confines of the definition of a boardwalk. That said, the design premise for the structural engineer is the exact same as if it was a pedestrian bridge. It's a short span. They had to span 9 meters. The architect was assuming actually they were going to purchase it from Bridge. But Bridge, who are wonderful, and you've seen all kinds of their stuff around, they're a little bit hard to get a hold of. And once you hand off the bridge to them, they design it. You lose a lot of control. They will say, okay, here's the cheapest, simplest form to get you from here to here and meet all the safety criteria, and that's it. And this particular one, they wanted the actual slats going across, or the decking surface is actually the rusted steel look as well. So custom bent shapes with tread holes punched into them. So another thing that's kind of ubiquitous from Bridge here in Ontario. So they found that they were being told by Bridge that they needed a particular size. It also came out that it was because that's what Bridge had on their lot, and they were just like, you're going to get the cheapest one if you do this. And their point was, we don't want that size. We don't want that to be what we want. Also, when I looked into it with the spans they were showing, it didn't work for vibration. So I sat down with the architect and said, well, we can do this in a way that any steel fabricator could bid on it, including Bridge. And Bridge now doesn't have to do the engineering because the engineering's done, which is a big component of their fee. So if they've already gotten me to engineer it, it can be a little bit easier for Bridge to say, okay, now we're just building you a bridge. So here you go. We can give you exactly what you want. So this is what they had originally assumed. These are sonotubes or caissons or piers. The original design did not have these two in the middle, and they were spanning the full 9 meters. And I'll show you what kind of shook out of that in a minute. Here's a cross section of it. They kept it low to the ground. It was just high enough that they needed a guard on this side, but on this side they didn't. There's a little bit of a floodplain here, and my understanding is it's only kind of spring and fall that this gets kind of gucky. So this was the first design. For strength, they needed a 254 by 152 by 16, which was that's Malcolm. We'll trade off. You bring him down because then you have to talk about a bridge. So bring him right down, okay? He's coming, buddy. So buddy. So that worked for strength, but it didn't work for vibration for that length of span. When I went through the process, I found that we needed a W310 by 129. A little bit harder to get, a little bit more expensive to install, less likely that somebody like Bridge would have it on site. We now needed to worry about torsion elements. We'd need a kick plate here to stop this from trying to twist because our guard would want to kind of deform the bottom of our W section. So you can see here that So our criteria for this span was we had 10% of acceleration due to gravity. So this was the criteria we needed to meet. And over here, for another runner with a walker at the middle, this kind of became the governing element here. So I talked to them and I said, what about putting a pier in the middle? It still didn't prevent the floodplain. The city was okay with dropping an extra pier in the middle there. And so we went down to a 203 by 152 by 6.4. So a lot smaller. It cleaned up the edge detail here just to add these two little piers. So now we have two 4.5 meter spans. But look, our criteria changes. Now this was what we needed for strength now. When vibration doesn't even govern, you can see that this isn't even close to the 15% limit that we had on this. You know, the criteria changes depending on our weight, which was related to what the weight of that member was. Our frequency changes, which is really how we determine our vibration, because that's related to our period. So this was the period that we measured, which tells us what the natural frequency of our bridge is. And you can see that the allowable peak acceleration varies depending on what you're talking about or how uncomfortable they'll let you feel. And so in the end, here are the drawings. You can see that we had, can you see it? Yeah, so there was soil criteria. The soil was really crappy in the upper reaches of this project, and it was really good down low. Luckily, the common type of foundation for small elements like this is caissons or sonotubes with reinforcing. So that worked out really handy because that was the exact appropriate solution to solve our soil problem, and it's the typical kind of precedent for designing these foundations. These two caissons here are bigger than the end ones. You can see that they're taking half of the bridge load each, or a quarter of the bridge load, and then these ones are each taking an eighth, or this quarter of the end of the bridge. In our condition where we only had 4 bearing supports, we had 4 sonotubes this size, 1 at each corner, because then they were each side was taking half of the bridge. When you add a middle support, you do not end up with a smaller foundation at that location. Because this location here is still taking half of the entire load of the element. It does move it into the middle, and these ones here can be smaller. It's the same premise when we're doing a stair. If we have outside stringers, people always say, well, what if we add a third one in the middle? Well, if these ones were too big, you're still just getting that big one in the middle because that one is still taking half of the entire stair load. So this is the next one. Dave, are you ready to come in here? So this one's the Aurelia Fishweir Bridge. Should I go get him some food?
Yeah.
Okay. Dave will take over talking about this. I'll come back.
Yeah, but I'm going to take all the space. So the Fishweir Bridge, this was a design competition, I believe, or maybe it was Shim Sutcliffe was hired for a concept regardless. In Aurelia on the Narrows, the Atherley Narrows between Lake Simcoe and Lake Couchiching is an archaeological site that's over 4,000 years old, that predates the pyramids, and it's a fishweir, a series of vertical posts driven into the riverbed that the indigenous people would have used to corral fish, and the place was considered a place of plenty. Champlain wrote about it in his journals. So it was a very sacred place for the natives, and and the town wanted to celebrate that, hired Shim Sutcliffe to do a design for a pedestrian bridge that would create a sacred place. This was their concept. So a series of closely spaced vertical poles that were intended to reflect the weirs and also generate something that's iconic. This was our concept for this. This is an inverted Fink truss. So forgive me for using a name. What a Fink truss is, it's not hard for us to picture a king post truss. Top chord, post in the middle, and V-shaped bottom chord. It's not hard to get our heads around how those work. Now, what if we take this as a king post truss and overlap that as a king post truss, and then overlap another one, and another one, and another one? What we wind up with is this series of interconnecting king post trusses that form a Fink truss. And the traditional Fink truss looks like the image that's on your screen here, but upside down. So a series of king posts. Post, cable, cable, post, cable, cable. Trouble with a Fink truss in a traditional bridge is it's deep, right? And so you are using up the headspace for the boats that have to navigate under the bridge. So that's one challenge with the Fink truss. It happened that in this particular project we had abutments at the end, but we had an existing train bridge that went across here, and so there were two abutments at roughly the 1/3 points across the river. What that means is that where a typical beam sags this way, over a support it sags the other way. So in the span the bottom is in tension, but over the support the top is in tension. So if we're going to do a Fink truss, we would naturally invert the Fink truss over top of the supports. By pre-stressing the Fink truss, we at the ends, pulling down the ends, we can make it so that it's in a hogging moment through the whole span, meaning that the top is in tension, the bottom is in compression for the whole span. What that does for us is it allows us to invert our Fink truss using compression elements that are vertical and tension-only elements that are on the diagonals. So that was the concept for the Fishweir Bridge. This is our structural analysis model, so crudely rendered, but you can see the idea, and you can see that it all ended up working structurally. It worked fairly well. We did wind up needing two very large girders. These were the bottom chord of the truss, for one thing. So the bottom chord is in compression, and so these elements needed to carry the compression. But they also serve for erection. This truss is going to have to be stick built. This truss is going to be stick built, which means it's not prefabricated as a truss. It's brought in piece at a time, in which case we need a platform to build on. So the bottom chord of the truss would have been would have allowed them to build almost like a staging platform, and the balance of the truss erected.
And the reason that works is because the load conditions during construction aren't the full use loads. They don't worry about vibration. They don't worry about serviceability during that stage. So the criteria are much lower, which is why you can use just those chords temporarily for that part of the construction.
Yeah, just the live load. We designed for about 25% of the live load in construction. So for the life of the structure, the live load is the densest possible accumulation of people. Whereas during construction, there's a recognition that it will be lightly occupied, and we generally
probably not having a party on it in the middle of construction. Although I've seen that.
Yeah.
Okay, so these are we're now to the fun part where we just look at pretty pictures. And we're going to try to not make this take too long. I think we have like 30 bridge images, maybe even less than that. I reached out to two prominent architectural bridge designers that work in Toronto. We have some kind of two world-renowned ones right here, and they shared with me a bunch of their images. Dave found a site on the internet that was like the top 22 scenic pedestrian bridges you must visit in Ontario. And we kind of laughed about it because it came up in our feed, probably because we were looking at bridge images. It came up in our feed for Facebook, so we were like, all right, let's check it out. But she was right. They were kind of the best ones we wanted to look at, so we incorporated a bunch of those into this as well. So the first one, this isn't one of the specific bridges. This is a bridge type. This is called a Baileybridge. These were invented in World War II by the British military. The idea being that you could bring it in components and you could manhandle them into position. They were brilliantly engineered, refined down to the barest minimum material needed to support the load, with constructability, fast constructability, with physical labor being the only use for construction. So you could have some tools, but the idea was that people would carry these with them to the site and install them on site. So these were military bridges for the longest time. Here in Port Hope, where we live, in fact, the Army did a training exercise a year and a half ago where the old Baileybridge had hit its life cycle. Because these are refined so explicitly, they are very adamant that they get taken down at the end of their expected life cycle. So the local Baileybridge in town was closed. The Army came in and dismantled it as a training exercise. And then they had a construction crew partnered with the Army who reinstalled it, a new bridge, a new version of the Baileybridge. So these are kind of ubiquitous around the world. You see these literally everywhere around the world and all very similar to this. You can see that it's very small members, allowing for this to kind of get erected easily and quickly. So here's just literally a brochure package from Baileybridge, or a Baileybridge manufacturer. Most of you have probably seen covered bridges. I wanted to show one of them here, mostly because they're quite common, especially in the Atlantic provinces where I'm from. This one's actually one from Newfoundland. Do you know why they bothered to cover the... Oh, do you know why they would bother to cover just the bridge? The road's not covered. What?
It's a good point. I mean, it's obviously to keep the snow off, but you're right.
But I mean, this isn't enough to slide snow off the roof either.
Yeah.
But probably just to keep it off the bridge itself. But you're not keeping the snow off the road.
Yeah.
Quick freezing because it freezes faster, but the rain not freezing. It's a question I've always kind of wondered, why bother covering the bridge?
Yeah. And probably when they were building these, the bridges wouldn't the normal bridge wouldn't support snow clearing equipment.
My guess is when they were building these, they were building with stick frame elements of wood. To be strong enough, they had to be quite deep. And once you needed it that deep, you needed to brace the top so that the trusses just didn't go bloop and flip over. And then you tied them together, and at that point, might as well cover it. So it's probably some combination of those two things.
So this is... Yeah, go ahead.
Oh, go ahead.
I was going to say, this is a very common truss form for timber trusses. This is the one that I always think of as the how, but in the diagrams earlier, it looked like the child's truss. But compression elements are double, two side by side, and oriented on flat this way, so that they're very stable in horizontal buckling. And then the tension member is diagonal. Actually, sorry, that's not true. It's also a compression member the other way, but helping to resist uplift So that's this one. Is designed to be able to carry compression, but only very nominal compression because generally the loads are down. And the tension members are all vertical. So these kind of rusted lines are the vertical rods. And these are extremely pragmatic from an assembly point of view and a connection design point of view. So they look more complicated, lots of different pieces going this way and that way and slipping past each other. But if we look at the connection details and think about the fact that they're built out of wood, this is a highly pragmatic truss, which is why they are so common.
Where every element is smartly placed in the right orientation, doing a very specific job to maximize every little bit of material and make it easy to build.
And when we look at modern wood trusses, what we see is big side plates with hundreds of bolts. These, the connection is just a rod goes through the cord with a washer and a nut, and that's it. So the connections are much, much simpler.
And right here, it's just a through bolt right through all three pieces, because those are allowed to, in fact, they have to be able to rotate relative to each other. I liked this one because it's one we didn't really talk about in the kind of common pedestrian bridge types. It is a concrete girder bridge. You see them quite often on highways where they're either precast or specifically cast. They'd be precast, usually hollow or precast T elements out of concrete. But this was kind of fabricated in a shop and then brought by crane. Usually pedestrian bridges, just the length of them and funding, and it being a one-off, this is not the normal style of construction. Normally when you see those concrete girders, you've got like 3 overpasses and one contractor's bidding on all of them. And so it becomes kind of economical for them to do that full set of them. This needed a big crane to come into sight. Usually access is an issue to get to these places. Like I know in our river here in town, they would damage a lot of the kind of existing infrastructure to be able to get a crane in close enough to lift something like this in over the bridge.
So trestle bridge, we certainly these are extremely common. This is a bridge that does not need to be a clear span, probably because this is not a navigable waterway. So if it's a navigable waterway, you need a big open span there to get the boats through. If it's not navigable, then a trestle bridge is just fine. All we're trying to do is create a flat path for cars and pedestrians so that you don't have to walk down into a ravine and walk back out again. And so we do a trestle bridge, and the advantage of a trestle bridge, very short spans. And if you remember Shannon's talk on one thing or another, talking about the reason why we do trusses is to avoid bending, because axial loads are much more effective than bending loads. So if we can build up this base infrastructure and shorten those spans and avoid a big girder, then there's a real advantage to it.
And this looks so busy because wood, as we've seen, is kind of our weakest material. But it's cheap and easy to build with, so you can bring it into sight. So what they have is a series of kind of freestanding piers lined up side by side. These bracing members that make it look so busy are keeping those from all just tipping over like a set of dominoes in every kind of kids movie or classic movie you've ever seen, where you've got a series of elements and one tips over and they all go down. So these are bracing those together to prevent that from happening. This is an interesting kind of aesthetic bridge where they light up inside the railings. It doesn't look like the railing is actually structural. It's doing its guard work, but even these just look like infill panels, that there are hidden inside the 2 pieces of panels a kind of piece of upstand steel, and there's just a steel girder spanning across the gorge.
So this is an arch bridge. This is one of the reasons why we want to introduce our arch bridges. So an arch bridge, you can see that you know, we've got two options. We can put the structure below, or we can put the structure above. Where we have the ability to put the structure above, an arch becomes a possibility. And this is a true arch in the sense that the abutments will take the thrust out of the arch. So we've got strong enough bearing conditions to take the outward thrust so that this can act like an arch, and then we are literally just hanging the bridge deck. An arch is a funicular form, so we started talking about the funicular catenary and its need to deform to resist the load, the varying load conditions. In an arch, we have a funicular form, but it's deep, and so it's bending stiff. So we have two superimposed load-resisting mechanisms. We have the funicular arch, but we also have the bending stiffness, and that's what gives the arch its overall stiffness. Shannon mentioned this in the context of the covered bridge, that if you've got an upstanding element with compression on it, there's a potential for buckling. So arches are connected together with these deep webs, which stabilize it laterally. So this is the Bell Fountain Bridge. This is a suspension bridge. You can see that on the previous example, the walking surface was the cable. In this particular bridge, the cable had more shape to it than the previous example, so it would have been too steep to walk on top of the cables. So the deck is dropped flatter, and the various crossing elements are suspended from the cables, as opposed to the deck sitting directly on the cable. We've got a series of hangers that pick up the crossing beams.
That then also conveniently become the guard.
Go ahead.
You ready to go?
Yeah. Okay, this is the one that Shannon was mentioning earlier. We went and visited this one yesterday. It's extraordinary, and it's only an hour and a half outside of Toronto, over a big wide river gorge. And this is a true suspension bridge in the sense that the structure is just the cables. So very, very shallow catenaries, grating as a deck that sits on top of those cables, and you can see the crossing beams that pick up the grating stick out several feet with diagonal braces. That's to support the guard. So all of these things, which are kind of the visually dominant element in a way, are there for the guard, and not for the catenary itself. The thing to bear in mind about a catenary bridge, this looks like a panacea, right? Like why wouldn't we just do this all the time? Very, very shallow, very long spans. The reason we don't do it all the time is that the abutment force is a function of the sag angle at the beginning. And if we have a very shallow sag angle, and let's assume it's 1 to 20 because that's the maximum permitted slope for wheelchair access. So it's probably 1 to 20 is the steepest angle. What that means is that the horizontal force is 20 times the vertical force. So the horizontal force at the end of these things is gigantic.
So take whatever your load is on it, multiply it by 20, and that's what you're trying to pull out of the rock.
So it's a terrific bridge when you have the boundary conditions to allow to be able to anchor those gigantic forces. But if you were, and in this case, this is a river gorge through bedrock, so it's possible to develop those huge forces. If you're in a soil situation or weathered rock, or like there are lots of situations where those forces are just unmanageable, and
you'd have to cast massive amounts of concrete, which you see happen for suspension bridges, for major waterways with vehicles going over it all the time. Kind of at the midpoint ones, they balance each other out by having the other cable on the other side, but eventually at the very ends you have big, massive abutments.
The one other feature here is that we do have a continuous element here, and that's a steel channel, I believe, which does contribute a small amount of bending stiffness. What that does is it just helps to stiffen the unbalanced loads. So when there's one individual on one point, there isn't a very localized sag.
That kink that you would see from a tight rope walker, for example.
So this is the William Small Cable Stayed Bridge in the French River Visitor Center.
I just want to point out, it's hard to see in the image, but there is another one of these piers with these cables over here on this side.
So this is similar to a suspension bridge, but you can see by cable staying it and putting a tower here, they can balance the tension forces. And so the primary abutment is a downward force. These do need to anchor into the rock, and those are big forces that go down. But the other thing is they've got a lot more depth, and the more depth you have, the smaller the force. That's the...
While still maintaining this, they changed the walkway being that angle and used the pier to develop the angle to bring those forces down.
Now, where the previous suspension bridge was not controlled by vibration, and when you walk across it, you can feel it, this one is controlled by vibration. So this one would have, is a snowmobile bridge. So there's vehicles going across this all the time in addition to the pedestrians. And so it's vibration controlled. The cable stays are tremendous for adding strength, but this is a truss. And the truss gives it bending stiffness, so that it's not behaving like a funicular form. Okay, so another Shim-Sutcliffe bridge. Interesting. We've got two in the lecture.
They show up in all our lectures.
Yeah, that's right.
Do amazing stuff.
So this is the Ledbury Park Bridge from the 1990s, but it's amazing that it still stands up like it's a current project. And this is a Vierendeel. It's hard to find examples of Vierendeels. Vierendeel, if you remember, is a truss with no diagonals, and because it has no diagonals, all of the web elements and cord elements have to work in bending to resist the shear.
Which means everything is a moment connection, which are expensive and hard usually.
So far less structurally effective. But Shim-Sutcliffe solved this problem by introducing very closely spaced horizontal elements.
Which they would have needed for a guard anyway.
With little blocks that go through that act like the web elements. And so because this little block, even though it's in bending because it's carrying shear this way, it's so short that the bending force is very small. So this wound up being quite an effective truss, even though it's a Vierendeel. I'm not sure how they get away with the climbability on this one. There have been interpretations that if the gap is small enough, it's considered not climbable, and I think maybe that's the answer.
I think these are on a slight diagonal, that it would be hard to get your foot on them. It looks like it from this image that they're on this This was built in the early 90s, before Dave was doing most of Shim-Sutcliffe's work. But doesn't it look like they're on a slight angle? That would make it a little bit harder to kind of get up on. You can imagine if they were tilted away too.
But also, it's a bridge, right? So the bridge isn't governed by the building code.
No, and that's true.
And so this climbability may not be a requirement in the bridge code. You know, the building code and the bridge code have a lot of parallels. Like the forces are very similar, and the guard forces, the standard guard height. But there's a few distinctions. Climbability may be one of them. If you're riding a bicycle across it, you need a taller guard. That's another. So it's I think a 1.5 meter guard instead of a 1.07 meter guard.
Another Eagle Bridge. What I like about this one is beside it you can see an old concrete arch bridge right beside it there. That one's the train bridge, correct?
No, that's a vehicle
That's
bridge.
the vehicle one.
Yeah, that's the cars going on.
So this is an Eagle Bridge, kind of that standard form, a basic truss. and then the guard infill.
The Eagle bridges are always HSS sections, and HSS is more expensive than open wide flange sections, and yet Eagle Bridge, who build bridges like they optimize them to absolute minimum cost, they always use HSSs, and the reason is that in an exposed environment, the HSS, if all the welds are fully sealed welds, presents the minimal surface area relative to cross-sectional area, so they stand up very well. It's a high longevity.
And as I've discovered, they mass purchase 3 or 4 major sizes and keep them in stock in their shop or in their backyard. Which is a fair thing. Like if you can buy 1 or 2 major things for cheap because you buy so many of them and you build it. That's the kind of the premise of open web steel joists, you know, like it might be slightly over designed for some of the elements or even a bunch of the elements, but it becomes cheap because it is the repetition. And with the Eagle Bridge, your repetition isn't in your bridge alone, but in everyone having a similar bridge. Mm-hmm. So you're getting that kind of cost effectiveness of repetition spread out over you and a bunch of other people. So these are some of the bridges that we haven't worked on that, 1 or 2 of them in these sets going forward. But these were sent to me, the DTAH ones were sent to me by Mark Landridge from DTAH, who's a fantastic bridge designer. And so some of these are concepts and some of these are built conditions. But he designs bridges all over the world. I don't know where this one is. I think most of the ones he sent us were actually in Ontario. Maybe some of you know this, but here's what I like. Dave talked about if you raise the bridge up, you need to get to the bridge. Look at the ramp needed to get up to the height to enter the bridge. The stairs are over here. This is the ramp required. It's almost as long as the bridge itself to get up to the bridge height so that it's accessible.
So you can see the minimizing structural depth becomes a real thing. Every foot of structural depth corresponds to 20 feet of ramp, so making the depth shallow makes a huge difference. So these are our box girders. So this would be a steel box girder. That's the bottom flange. A web on this side. There'd be a corresponding web on the other side. The top flange may be the concrete deck. That's a very common way to build highway bridges. It's very likely the way this was built. So the top flange of the box girder is the highway deck, and the columns are also box girders. This is a very typical condition here. You can see that the flange overhangs the web by a small amount. This is so that you can weld them with a fillet weld. A fillet weld is very effective when you've got 2 things coming in at 90 degrees to each other. You fill the little gap with a fillet.
The one thing about a fillet weld often is we usually like them in situations where it's upright or sheltered somewhat because water can pool in there. So this fillet weld right here and this along here, that's where we're going to get standing water. So that needs to be kind of ground smooth and painted to make sure that we don't have any chance of rust, because that's going to be the weak spot on a system like this.
Mm-hmm. That's a good point. This is a painted bridge. Paint is most vulnerable on the sharp corners, and they probably had to grind all of the corners to about a 3 millimeter radius. All the welds would have been continuous as well, rather than stitch welds.
So these are kind of built up on 2 V's that you can imagine aren't stable by themselves, but they're great for supporting loads. But because we have, it's so hard to look at yourself in this, because we have 2 of them, they're starting to balance each other. They become a braced system where they're balancing each other out.
Okay, this is an extraordinary. This is the Garrison Crossing at Fort York. This is a DTAH's bridge. Stainless steel bridge, single-sided arch. And you can see what they've done here, which is quite interesting. The hanger cables cross each other. By crossing the hanger cables, the hangers are now able to transfer shear, horizontal shear, between the top arch and the bottom chord, which is the deck, which means that the whole system acts like a truss. Not only do we have a girder or have an arch, but we have a truss, which stiffens things up significantly and assists in mitigating vibration.
And it can reduce the top chord. It's not as much a bending element anymore.
That's right.
This is so kind of compared to that wood element.
Yeah, you can see the guard condition here. It's an expanded cable mesh. The guard is higher than normal, so this is the 1.5 meter guard that I was talking about, or maybe it's up here actually.
That's the 1.5 meter.
That's the 1.5 meter.
You can see where it starts.
No, this is
higher.
This is even higher. Yeah, so these are higher than normal.
Over rail bridges. They often, especially in large kind of metropolitan areas, will often extend the guard even more to kind of prevent people trying to commit suicide.
And throwing trash.
Yeah, that's true. But so it's adding a barrier. It's adding a barrier to the system.
So this is a really lovely bridge. I'm a reluctant admirer, and I am a reluctant admirer because we were on the team that was not successful for this project. This is a straight bridge with a single-sided arch. The interesting thing about that is that, so we've got the single-sided arch, and on this side we have our deck. Our load is out here. Our resistance is here. Our load is here. Our load is in the middle of the deck. Our resistance is in the arch. So the whole thing wants to twist. The torsion, so the bridge deck itself is twisting like a shaft. That torsion is coming out into the abutments, and the bridge itself has to be made torsionally rigid. So the bridge is a big box in order to give it torsion. Or
solid cast concrete where the reinforcing is doing that, but those are the options. Yeah.
So we move on. This is the one that we were involved with. This is the
that didn't win.
the unsuccessful version. This one you cannot see quite, but this one is curved in plan as well as an arch. And if we consider the arch this way, the curve is under the arch, so that when you look down and plan, tip the arch off, it creates a curved crescent-shaped profile, the plan projection. In this case, the deck followed that. This is a really unusual way to build this type of bridge. Often there are declined arch bridges, often with a curved deck, but typically the deck curves opposite. And the idea is that the eccentricity of the arch balances somewhat the eccentricity of the deck. We rationalize that the weight of the deck is small relative to the weight of the occupants, and so curving it to follow the arch wasn't a problem. And architecturally,
and you analyzed it too.
Well, obviously, yeah, we improved it, but it was architecturally consistent with this idea that the arch and the deck represented the erosion of the river bank through an S curve, because this is the site of the original Garrison Creek.
So you can see that it continued along with another bridge over there, kind of creating this flowing S curve.
And what we did here, and this will be obvious actually in this next image, what we did here is we introduced these vertical standoffs off of our, which essentially took the line of force for that cable down through the middle of the bridge to reduce the amount of eccentricity. You see we've got in our deck, we have these two big pipes, and so those two pipes make the deck torsionally rigid. And then ours was a big curved pipe arch. You know, this is one of the lessons learned. We felt that the bridge needed to satisfy the most stringent vibration criteria, and so this is quite heavy. You can see that our cord is fairly heavy, and our bottom cords are quite heavy. The winning bridge, I'm fairly certain, doesn't meet the same vibration criteria. Perfectly adequate vibration criteria, but I think that we set the bar too high, and the design paid the price for it.
It's tough in competitions because you want to make sure you don't undersell and oversell simultaneously, because they could have found that they had gone with the lesser criteria and had a client who was upset by that.
Yeah.
It looks like the winning team
and
satisfied that.
That's right.
Way. Yeah.
And it was a design build competition, so the contractor was on the hook. Like, it was a fixed price, and so to go in with a lower vibration criteria and then have the higher criteria imposed on you afterwards would be a real problem.
Yeah.
And these were the abutment wraps. This we've included for fun, in a way. For one, to show you, I mean, the kind of infrastructure that's built, that has to be built for the to accommodate the abutments.
They're also all each little mini pedestrian bridges.
They really are, and so we detailed them in the same way. It's the same two tubular sections with the K bracing for the web. This is something that I really enjoyed. So the architect had an idea of a single line of support down the middle, but of course we had to support two edges. So somehow we had to take the single foundation and bring it up to pick up the two edges. So we did something playful, and we made it look like a Y, and a Roman Y. Like, we actually took the explicit form from historic typeface, which would have been appropriate around the time. Y for York, obviously. So this is the Humber River Bridge, another Montgomery and Sison bridge, and this keeps showing up as an iconic bridge. It was in the 22 best scenic bridges.
But Bob Davies had already given, like, this is a picture directly from Bob that he sent me to include. So this was built in the 90s, correct?
Yeah,
it's 30,
early 90s, I think.
It's 30. I know it's 30 years old, but it holds up with the kind of current modern bridges to this day. It really was kind of cutting edge at the time.
Yeah.
I don't know if any of you have ever gone across it. You can feel vibration, but I've been on a lot of Eagle bridges that you can feel worse vibration than this.
One thing about vibration, actually, is that we talked about the impact of mass, which reduces amplitude but lowers the frequency, stiffness, which increases the frequency. The other major component of vibration, your vibration sensitivity, is damping. It's how quick does the wave die out? In steel elements, in an all-steel bridge, you've got almost no damping, and so that part of it becomes a real challenge.
So this is not one that we worked on, but Bob Davies from Montgomery Sison did send me this one. What I like is that it's a Gerber girder system. A Gerber girder system.
You dropping names?
A Gerber system is when you have two elements that cantilever out past a support, and then you just drop one little piece in the middle, which is often how we build bridges, but I just like how visible it is here. This was a section that they erected, and they could build across it. This was a section that they came across and built. And then they could bring their equipment here and drop that centerpiece in and keep building across. They could finalize that building across.
If we can picture the bending moment diagram for simple spans, simple span bending moment diagram, WL squared over 8, WL squared over 8. Okay.
Open the drawer. You can keep talking.
So simple span bending moment diagram, peak bending moment moment is WL squared over 8. if we introduce continuity over the supports, so we don't let it hinge at the support, we wind up with a hogging moment, a negative moment over the support, and the peak moment at the support is now WL squared over 12. So it's 50% less than, or a third less than the moment that you would have in a simple span. The deflection, so that's the strength criteria. The deflection, I think, is about an eighth of the deflection that you would have.
So the top one is our normal WL squared over 8 bending moment. You can see that we have it top and bottom, which means we have to worry about some lateral torsional issues. But on a bridge that's wide, those problems tend to go away, or they can easily go away if you make it a box girder section. And then you were talking about deflection. So
yeah, if deflection and vibration are the things that control the design, which they very often are in pedestrian bridges, it is dramatically stiffer by having continuity over the supports as opposed to letting it hinge at the support. This is another Montgomery and Sison bridge, this one from the 80s. So this is built as part of the Sky Dome. And this is a cable-stayed bridge over the rail corridor. Cable-stayed arch bridges, these bridges have the advantage that it puts the structure above the bridge, not below it. And by putting the structure above the bridge, you maximize the space underneath. So this bridge had it was above a rail corridor, and so the space underneath was critical. So 2 towers and cable stays.
Because this was in the 80s, kind of our experience with architectural steel or visible structure steel was kind of new and not that normal. So you can see they kind of were quite playful in what they did. At the time, this was really cutting edge steel work.
Yeah.
This was not done. Now we kind of look at it and it seems a bit frilly.
Yeah.
But at the time, it was kind of not much like it.
Yeah, these big gussets with lightning holes in them are a bit of a postmodern move, aren't they? We see them like all through Metro Center and everything at the time.
What I really like about this is just showing kind of the side, like to get these beautiful thin little cables, you still need to connect them, and that's kind of where all the hardware comes. So we're not gonna talk about this really right now, because next week you're gonna talk a lot about hardware in your fabric lecture, which is gonna be a long one, but it's a good one.
Only because it's awesome. What I just realized is they've got a swivel built in here.
Yeah.
So that this is a double articulating joint. So that the standard bridge fitting articulates in one direction, rotating about its pin, but they've introduced a swivel here so that it articulates about that pin as well. We had these elements on our Under the Gardener scheme,
which I did. Dave's a little bit sour that I did not get these into the slide. But he didn't give them to me. I don't know where they are. I don't know. You had those in your Under the Gardener bridge.
Yeah.
I guess that was the end of that. So this one must be this is a competition. I can't even. So Bob sent me this image. I can't even find any reference to it on the internet. So I hope he didn't sign some NDA on this and just forgot and sent it to me. But we were looking at it and we were like, well, how is this? How is that moment connected? Because to support this, it would need to be moment connected. And all we can think is that this, even though you can't see it here because it's an early rendering, must be a lift of some sort. That this must lift up to allow boats to pass through. I feel like this is a very early rendering, and that this would chunk up as kind of things further develop. And again, how this is actually secured in this shape. Maybe with cables back here is what I can imagine.
I'm guessing this is a big counterweight here.
Yeah. To make it easy to go up and down.
Yeah.
But there doesn't seem to be hinge here that allows those two pieces to go up.
Lots of pressure.
Press Bob on this. So this will be cool. I'd be intrigued to see kind of where this goes in the wall. This is more what I expect to see
from a lift bridge.
From a lift bridge, exactly.
Now this was a vehicular bridge as well.
Much bigger, a lot more going on, for sure.
And this actually was this was actually approved, and then they canceled it and then built the tunnel underneath. Right?
Yeah, like this was how it was going to go, and then they changed it. Did Montgomery Snison do that?
No, ZAS did the tunnel.
So Bob Davies is the one who sent all of those bridge images to me. Bob has a cottage property. Where is it? It's So unlike most people who find a lake and plop their cottage beside it, Bob found on an old logging trail a little property on a creek. And I have to say, I've been out there, and it is stunning. It totally changed my idea of what a cottage property could be. But he has a little creek, and in the middle of summer, like, you could almost jump across it. When we were there, it was before they'd even built the main cottage, and they were still, it was like this old kind of log hut. They had like an old door, I think, sitting across the river. So it's at times it could be quite small, but in the spring it would rage. And he actually has sent us pictures of his property flooding almost right up to his door in one of those years where they had just massive torrential rains. But Bob wanted something unique, and Dave and I also give a series of lectures on reciprocal frames, which are self-supporting structures, which sounds bonkers, but really you make a continuous framing system piece at a time and a piece at a time until they connect together.
So yeah, what's the definition? A self-supporting network of interconnected elements or something? So this particular diagram here was drawn by Leonardo da Vinci in his Codex Atlanticus. I was really taken by this when I discovered it for our reciprocal frame lecture, and have since realized that there's a bunch of people that have built these. It's sort of
it's a hobby. Like, people build these with their kids.
Yeah. Here's the diagram. So no one element spans all the way, but by virtue of the fact of their interconnection, they create a continuous spanning element. And
so Bob's is more this stage right here, but he didn't need that because he only needed to span that far, and he did it in just 2 segments. You can see here there's that portion and that portion. I love this image right here.
Yeah, it's really wonderful. And the idea is that you get, he needed to span farther than a single piece of timber would span. And that is the rationale for doing any reciprocal frame, is that you need to span 30 feet with 20-foot timbers. Well, you make them a reciprocal frame and interconnect them.
And we do it all the time when we build spliced built-up members. But this used to be quite common. Reciprocal frames for buildings, bridge structures was quite common, back in the 1800s and before, when we were limited by wood as our available building material. But once we started creating our own materials, it kind of fell to the wayside. And we're kind of seeing a resurgence of it. I mean, between the two of us, we've done how many reciprocal frame structures? Like
several, anyway.
Lots. I mean, we have enough that we've gone to Finland and given a talk about it. We don't get to go to Australia, but we're giving a web lecture in 2 weeks to the wood conference in Australia. So reciprocal frames, not going to save the world, but really friggin' cool. So what are the takeaways for pedestrian bridges? Well, often vibration is the controlling design feature. The depth of the spanning members is often governed by the spanning length. If you're for whatever type of spanning member you're talking about. If you're talking about an arch, well, you can start to play with it. But if you're talking about a truss or a beam spanning across, your depth is going to be related to your length. You can use beams, trusses, cables, or combinations to span across that length in kind of whatever way works best for your form and your intents. And do you have things passing underneath? Do you have things passing over? Kind of can give you, there is no right answer, and each context is going to have its own correct answer for a pedestrian bridge. Okay, it got light, kids are up. We will try to, or one of us will record the post lecture sometime today, and then hopefully tomorrow we can get a week ahead and post the fabric lecture. All right,